So far, we were able to design circuits of very reasonable depth and size for 3 of 4 arithmetic operations, and the only one which is left is division. We'll learn how to perform this with circuits for integer numbers. We are talking now about getting the integer part of the ratio of two numbers and the remainder, division with remainder. And although we'll learn how to divide integers, to actually perform this, we first need to generalize slightly our existing three operations into rational numbers of special form. So the rational numbers that we will be talking about, they are of the form p over 2 to the power of k, where p is an integer and k is a non-negative integer, and so we have the fixed form of the denominator of this rational number. To transmit this number between circuits, we need just to keep binary notation for p and binary notation for k. And as soon as we keep all these things, we are able to easily multiply numbers of these forms. So if we have two numbers, p over 2 to the power of k and q over 2 to the power of l, say, their product is the product of p and q, which we are able to do with logarithmic depth. And in the denominator, we'll have 2 to the power of sum of k and l. And we are able to sum integers easily as well in logarithmic depth. If we are to add these two numbers plus q over 2 to the power of l, if we assume that k is greater or equal to l, then this number is equal to p plus q times 2 to the power of k minus l over 2 to the power of k. So dealing with summation of such numbers is essentially comparing numbers, checking which is greater, because here in the denominator we'll have the greater of the two denominators. Now here we have subtraction, and we have addition. So multiplication by a power of 2, by a non-negative power of 2, is essentially the same as shifting and padding with zeros. So everything here is doable using just the same machinery we already learned, because we can separately deal with denominators and numerators of all these fractions. So we'll now assume, without further comments, that we are able to work with such numbers in a given depth and size. So for all such numbers, we have addition, subtraction, and multiplication with size, which is big O of square of the binary representation of these numbers. So if we have numbers p, q, k, and l, so if the maximum of these numbers is storable with n bits, then we have size at most quadratic and depth at most logarithmic. So assuming that all our numbers p, q, k, l fit into n bits. So now let's formally state the problem of dividing two integers. So we have two integers a and b, and we'll assume that they are greater or equal to 0, b is non-zero, and all these integers are n-bit integers. So we are to find integer numbers q and r so that a is equal to q times b plus r, where q is the quotient and r is the remainder. Well, of course, q can be expressed as a over b and floor function. So finding q and r is our goal, and to do so, we'll employ a technique for numeric solution of equations. The Newton's method for solving an equation, f of x is equal to 0. So suppose that we are to find x for which some function f is equal to 0, And suppose that our function looks like this, that it's concave. So that's f of x. Now, suppose that we have some initial approximation x0 for the root of this equation. So what we do is that we compute the value of the function at this point. So we basically take the point x0 and f of x0, and then we draw tangent line to the graph of the function at this point. This tangent line intersects the OX line in some points x1, and we now repeat this process. So we take the points with coordinates x1 and f of x1, we draw the tangent line through these points. So this would be some other tangent line, it will intersect our OX line in point x2, and so on. So we repeat this process, and visually it's clear that this process allows us to quickly converge to the real root of the equation. But we need to prove this, and we need to discuss the quality of conversions, the rate of conversions, how fast we are approaching the actual root, and what it has to do with our division with remainder problem. So we see that the main thing that we need to compute is actually q, because as soon as we compute q, we can compute r as the difference between a and b times q. And subtracting and multiplying numbers are the things that we are already able to do. Now, how do we compute q? By definition, q is the integer part of a over b. It's the number such that q is less or equal than a over b, and a over b is less than q plus 1. So actually q is a pretty good approximation to a over b. And to get such good approximation, we'll do the following. We'll approximate the number 1 over b. So we'll compute a over b approximately as a times 1 over b. And the approximation that we'll have for our number 1 over b would be with special type of rational, with power of 2 as the denominator. So we'll approximate this number as some p over 2 to the power of k for some p and k, and then we'll be able to use multiplication, which we know how to do, to compute a over b approximately. But this would be enough. So let's now, in our Newton's method for approximating the root of this equation, let's now decide how we compute xi plus 1 given xi. So remember that x1 was the point of intersection of the tangent line at the points x0 and f of x0 with the OX line. So the derivative f prime of x0 is actually the slope of this tangent, and this is equal to the ratio between this segment and this segment. So this is equal to minus f of x0, this is the length of this segment, divided by x1 minus x0. So what we have here is that the same equation actually holds for arbitrary I. So f of xi prime is equal to minus f of xi divided by xi plus 1 minus xi. And solving this equation for xi plus 1, we get the Newton's formulas that xi plus 1 is equal to xi minus f of xi divided by f prime of xi. So far, it is not clear how this formula, the Newton's process, allows us to solve the division with remainder problem, because this formula itself involves division. But let's now take our function f the following. So let's take f of x to be equal to b minus 1 over x. Remember that our goal is to compute 1 over b with high precision. And actually, the root of this equation is exactly 1 over b. So now let's apply our Newton's process to this function. Now, if we plug in this function into our formulas, we get xi plus 1 is equal to xi minus b minus 1 over x. And in the denominator, we have derivative. And the derivative of this function is 1 over x squared. So here we have xi and xi. And we see that it is actually equal to xi minus b xi squared and plus xi. So in the end, our formula gives us xi plus 1 to be equal to 2xi minus b xi squared. So this formula no longer involves any need to divide. Xi plus 1 is equal to 2 times xi minus b times xi squared. So to compute the next term in our sequence of x's, we need just constant number of operation, which we know how to do. Subtraction and multiplication. Now we need to track how fast this sequence of xi's approaches the actual 1 over b, the actual root of this equation. Let's assume that we have the picture as the one that is shown here. So our first approximation was slightly less than the root of the equation, than 1 over b, and strictly greater than 1 over 2b. Well, actually, it's relatively easy to find such x0 without any using of division, because if we need x0 like this, we can just take a power of 2. So let's try to find x0 as 1 over some positive power of 2. 1 over 2 to the power of k is less or equal than 1 over b and greater than 1 over 2b. Out of this, we can find that k is such that 2 to the power of k is less than 2b and greater or equal to b. So it is relatively easy to find such k. We're just looking at the number of leading zeros in b, and we can then determine the actual power of 2, the smallest power of 2, which is at least as large as b. Thus we determine k, and thus we determine x0.